Let's see another illustration. A particle of mass m and charge q is projected into a region having a perpendicular magnetic field B. Find the angle of deviation of the particle as it comes out of the magnetic field if the width d of the region is very slightly smaller than a mv upon qb, b mv upon 2 qb, c 2 mv upon qb. Let's see the solution. The radius of path r equal to mv upon qb. For d less than equal to r, we have sin theta equal to d upon r. A d equal to mv upon qb equal to r. Therefore sin theta equal to mv upon qb upon mv upon qb equal to 1, or theta equal to pi by 2 radian. B d equal to mv upon 2 qb less than r. Sin theta equal to d upon r equal to mv upon 2 qb upon mv upon qb equal to half, or theta equal to pi by 6 radian. C d equal to 2mv upon qb greater than r. The deviation of particle is therefore theta equal to pi radian. Let's see another illustration. Electrons emitted with negligible speed from an electron gun are accelerated through a potential difference V along the x-axis. These electrons emerge from a narrow hole into a uniform magnetic field B directed along this axis. However, some of the electrons emerging from the hole make slightly divergent angles as shown in figure. Show that these paraxial electrons are refocused on the x-axis at a distance x equal to under root 8 pi square mv upon eb square. Let's see the solution. The velocity of electrons as they emerge out, half mv square equal to ev, or v equal to under root 2 ev upon m. The velocity can be resolved into two perpendicular components, v cos theta along x-axis and v sin theta perpendicular to it. The time taken to complete a circle t equal to 2 pi m upon eb. In this time, the distance travelled by electron along x-axis x equal to v cos theta into t equal to under root 2 ev upon m into 2 pi m upon eb cos theta. For small theta, cos theta equal to 1, x equal to under root 8 pi square mv upon eb square. Now let's see cyclotron. Cyclotron is a device which is used to accelerate positive charge particles like alpha particle, deuteron, etc. It is based on the fact that the electric field accelerates a charged particle and the magnetic field keeps it revolving in circular orbit of increasing radius. It consists of two hollow D-shaped metallic chambers D1 and D2 called Ds. The Ds are connected to the source of high frequency electric field. The whole apparatus is placed between the two poles of a strong electromagnet Ns as shown in figure. The magnetic field acts perpendicular to the plane of the Ds. First cyclotron frequency, time taken by charged particle to describe a semicircular path t equal to pi r upon v equal to pi m upon qb. The period of oscillating electric field t equal to 2t equal to 2 pi m upon qb, and cyclotron frequency t dash equal to 1 upon t equal to bq upon 2 pi m. Second, maximum kinetic energy of the particle A, we have r equal to mv upon qb. For r node equal to mv node upon qb, which implies v node equal to r node qb upon m. R node, maximum radius of circular path kinetic energy, equal to half mv node square equal to half m r node qb upon m square equal to q square b square upon 2m r node square. B, also kinetic energy equal to work done by electric source, kinetic energy equal to F into qv into 2 equal to 2f qv. Let's see another illustration. Two positive ions having the same charge q but different masses m1 and m2 are accelerated horizontally from rest through a potential difference V. They then enter a region where there is uniform field B normal to the plane of the trajectory. A show that if the beam entered the magnetic field along x-axis, the value of the y-coordinate for each ion at any time t is approximately y equal to bx square q upon 8 mv power 1 by 2 provided x remains much smaller than y. B. Can this arrangement be used for isotope separation? Let's see the solution for part A. The path of ion is shown in figure. The magnetic force provides an acceleration which is towards the center of path C. At any instant, the acceleration AC equal to F upon m equal to QVB upon m and AY equal to AC cos theta. For small x, theta tends to 0, cos theta tends to 1. Therefore, AY equal to AC equal to QVB upon m. For x equal to Vt, y equal to half AYT square. From above equations, we get y equal to half AY x upon V square equal to half QVB upon m x square upon V square equal to half QBx square upon mv. Since ions are accelerated through potential V, therefore half mv square equal to QV, which gives small v equal to under root 2q capital V upon small m. Now y equal to half QBx square upon m under root 2qb upon m equal to bx square q upon 8 mv power 1 by 2. B. From equation 3, m proportional 1 upon y. Therefore, m1 upon m2 equal to y2 upon y1.